Okay, welcome to the lecture on MRI the Basics, Chapter 6, Tissue Contrast and Clinical Applications for Biomedical Imaging 201, Principles of MRI. We're continuing here, building off Chapters 4 and 5 that we're discussing T1, T2, T2 star, and then TE, TR. And then now we're going to dig into, again, the same area, digging further into what drives this contrast and specifically what some of the definitions are of T1, T2, and proton density weighted images. First, we'll start off with this beautiful MRI picture for the day. This is a picture from diffusion tractography. And this is a more advanced type of contrast, but very commonly used for brain imaging to be able to reflect tracts of white matter in the brain. Here you see sort of a view on the right side here between the hemispheres and the connecting fibers going through the corpus callosum there. And the different colors in these maps represent the different orientations of the fibers. So really both look beautiful and they're very rich in information. So there's a huge, in fact, range of MRI contrast, including what was shown on the last slide, or the diffusion in the bottom right. That's going to be a topic in this course. We're going to cover if somebody does it in a research project, or I'll go through it at the very end. Nobody chooses that as the project topic. There's a couple sort of other advanced contrast mechanisms that we won't be explicitly going over, magnetization transfer weighted and MR angiography, but that are very practical. The ones we're going to cover in this lecture are going to be proton density weighted, T2 weighted, T1 weighted on the top row, and also on the bottom row, T2 star weighted and proton density weighted. And the gradient echo sequences, the differences between spin echo and gradient echo. It's just a couple chapters away, we're almost there. And then we will also be in the next chapter covering the, you see inversion recovery, this word used in a couple of the contrasts at the top. And we'll also be just covering in the next chapter this inversion recovery contrast. So the goals here are to actually look at what are the tissue characteristics that affect the T1 and T2 relaxation times, and then more specifically define T1 weighted imaging, T2 weighted imaging, proton density weighted imaging, and some basic ways we can identify these types of images. So first we want to get into what tissues have short or long T1s or T2. And the textbook has a nice explanation and a classification of tissues into 4 basic types. So liquids or fluids such as water, blood, cerebral spinal fluid. We have solids that we typically don't see on MRI for reasons we'll discuss, such as cortical bones, fibrosis. We have fat, and we have what so-called proteinaceous materials, so other internal organs, muscle. And so these are some rules of thumb for what affects the T1 characteristics of different tissues. So if you recall, T1 is the spin lattice relaxation time, or the exchange of energy between spins in the lattice. And there's this concept of protons having natural motional frequencies. And this depends on how sort of mobile they are, typically. So they have this motional frequency. And you have this almost like a resonance phenomenon, but you have the most efficient transfer of energy between the spin and the lattice when their natural motional frequency is near omega naught, is when near the Larmor frequency. Okay. So I'm going to give you what the natural motional frequencies is that, so for liquid fluids, the protons are very mobile, the spins are very mobile, so they have these very high natural motional frequencies. And actually this leads to very long T1 relaxation times. So the motional frequencies are actually not similar to omega naught, they're much longer. Now, solids have more of an intermediate T1. They have a much lower natural motional frequency. The protons are not going to be as mobile in the solids. Fat, it turns out, has a natural motional frequency that is very similar to the Larmor frequencies. So it ends up having some of the shortest T1s that we're going to observe. You can see that in the chart up in the top right here. You notice the fat T1 values really stand out as being short, whereas CSF, cerebral spinal fluid up there, stands out as being quite long. And then a number of the other tissues are in the intermediate range between these. And these are mostly the proteinaceous materials, your internal organs, and these have some intermediate T1 due to also a relatively lower natural motional frequency of the protons. So they're not similar to omega naught, they're lower. There's also a class of proteinaceous fluids, specifically edema is a good example of this. When you have a lot of macromolecules in these fluids, actually there's a shorter T1 than, say, more pure liquids or fluids, because the presence of macromolecules inhibits the natural motional frequencies. And so you actually get quite a bit shorter T1s because they have this natural motional frequency that is similar to omega naught. So I pulled this out here. This is kind of a special case. T2 characteristics. Again, we're going to divide it up into these different categories or classes of tissues. T2 is what's known as spin-spin coupling. So we have the reason for this is when you have stronger coupling between neighboring spins. This leads to more of the microscopic dephasing that we discussed in chapter 4, and thus shorter T2 values. So in liquids and fluids, actually the protons can move from their locations to minimize the spin-spin coupling. So liquids and fluids end up having very long T2 values. They're not shown in this table up here, but these are, we're going to see in image examples that in T2 weighted images, we always see high signal from fluids and liquids. Now in solids, there's very strong spin-spin coupling. The spins are fixed in their locations, so they have this forced coupling. They can't move to positions of lower spin-spin coupling, and so you get very short T2s that are actually quite hard to image. Fat, as turns out, is sort of in a range of, and also proteinaceous materials are in this regime of intermediate coupling, and so this is where a lot of our our internal organs and lipids fall into this sort of intermediate coupling regime. We have sort of intermediate T2 values as well. Okay, so a real quick refresher from the last lecture from chapter 5. How are we going to create this T2 or T2 star weighting? We're going to change the time between our RF pulse and our data acquisition. So, for instance, we could do, 1 echo time at a shorter echo time, and we're going to have simplicity. We'll say this is the same our 90-degree RF pulse. Tip down our Z magnetization. It's going to slow T1 recovery. We're going to create our transverse magnetization. It's It's going to decay with T2, T2 star. Okay, and the way we're going to modulate this T2 or T2 star weighting is by choosing different echo times. So we could also choose a shorter or a longer echo time, where at TE2 we get some signal that would be proportional to the magnetization when it's decayed due to T2 slightly more, or this echo time where it's decayed slightly less. And then I think the other piece to add in here is that we can have tissues that have different, a different T2 relaxation time. I could have another tissue here. We might have a different T2 relaxation time. And so the contrast that we create is in fact going to increase as we increase the echo time. So here's some of the signal expressions that capture this. And like we were talking about in the last slide, it's really these long echo times that create this T2 contrast, so what we refer to as T2 weighting. And when we're creating T2 or T2 star weighted images, we're usually trying to also remove any T1 weighting. So we're usually trying to make this primarily T2 weighted. So that means we're going to be trying to make this term be 1, for example, in this equation that we've seen in the last lecture. And we can do this if TR is much longer than T1. So that's what's described in the third bullet point here, is to create T2 or T2 star weighting. We're typically going to use a long echo time and a long repetition time. There's a slightly more subtle way to do this with the gradient echo, where you can use a long echo time and low flip angles. We'll get to that a little bit later. But we haven't gone into the case of arbitrary flip angles yet, but we'll derive this gradient echo signal equation a little bit later on. And really one key characteristic that defines T2 or T2 star weighted images is that we're going to see bright signal from longer T2s, which are primarily fluids in the body. Okay, so next moving on to T1 weighting. So how do we create T1 weighting? As you may recall from the last chapter, we're going to do this by adjusting the repetition time between, so the time between different RF pulses, to ensure that there's actually incomplete T1 recovery of the net magnetization. So, for example, we could do one separation of RF pulses by some repetition value TR1, or we could even choose a shorter repetition time as well. In these cases, our data acquisition is going to go. Now we're usually going to do short echo times because we don't want to have T2 weighting or T2 star weighting. And depending on whether we do a short or long repetition time will affect the amount of T1 contrast that we would get. So in one case, you might get more, and here I'm going to draw it in steady state. We might get some longer T1 TR, we will get more. So T1 signal recovery. So actually we'll get larger. Transverse magnetizations, or with a shorter repetition time, there'll be less time available for T1 recovery. So I'll end up with smaller transverse magnetizations. So here we've created, by adjusting the TR, we've created a different amount of T1 weighting, and then these signal curves will also vary depending on the T1 value of the tissues of interest. Okay, so again, what we're going to do to create T1 weighted images, we're going to apply short TRs and high flip angles, and this is going to create T1 weighting. And we're also going to want to remove the T1 weighting. So now here's the equation we've derived over on the right here on the top, the one that says spin echo. And in this case, now we want to make this term become 1. So to do that, we want the echo time to be short. We want it to be much shorter than T2. And then we're going to retain just this other term here that's going to provide the T1 weighting. Okay, so T1 weighted then are typically with short echo times and short TRs. With the 90-degree flip angle that we've covered, we'll also begin to look at the case of arbitrary flip angles, which is this gradient echo signal equation where alpha is the flip angle. We'll cover that, and then it becomes, they have a little bit more ability to sort of do generally just short echo time and large flip angles and some sort of shorter TR. But the main point is that we want to get across is the short TE and short TR typically. And then what is characteristic of T1 weighted images is that now fluids, which have very long T1, which were bright in T2 weighted images, are now actually much darker on T1 weighted images because they have a very long T1. Whereas we get much brighter signal from things that have short T1s, and the main shortest T1 tissue are lipids or fat. So T1 weighted images are characteristically going to be, you can look for these two characteristics: low signal from fluids, bright signal from fat to establish it's a T1 weighted image. And then finally, we can go to proton density weighted images, which is basically no T1 weighting or no T2 weighting. So in this signal equation that we derived over here, we in fact want both of these terms to become 1. And so we're going to achieve this by choosing a long TR and a short TE. The intuition there is a long TR. We're going to get full T1 recovery, so no T1 weighting. A short TE, we're not going to allow any time for T2 weighting to accumulate. And in this case, then we're going to get a signal that's going to be reflective of M0, the proton density of the tissues. This is more putting up here for your reference, but you can plot these various signal equations as a function of TR over T1 and TE over T2. So the equation that we've really looked at so far is the top case, this 90-degree flip. Coming up next, we'll look at inversion recovery very shortly, and then later on look at the case of arbitrary flip angles. But you have this as a reference to come back to, and you can kind of trace along these curves to see the various trade-off between signal and also then the contrast is going to be moving along the different axes as well. Okay, so that brings us to the end of this rather short but hopefully informative lecture on the tissue contrast, some clinical applications. So key points I want you to take it home are referring what are the tissue characteristics of these different tissue classes that we defined that affect T1 and T2. So generally which tissues have short or long T1 or T2. And then the specifics of the different types of weighted imaging. How do we define and achieve T1 weighted imaging, T2 weighted imaging, proton density weighted imaging in terms of choosing TEs and TRs. And then I've given you a couple of rules of thumb to identify T1, T2, and proton density weighted images that will continue to build up that skill a little bit in class as well. Okay, thank you very much for watching.